Hi everyone. I'm going to walk through experiment one, the analysis of our data. And the expectation right now is that you've completed um, the data tables, like you've collected everything for each experiment and have used Desmos or some other, computer-aided graphing software to make a graph of your data for each um, experiment. So for experiment one, hopefully you have converted all the necessary units so that your forces are measured in newtons and your velocities are in meters per second. So when you graph that data, our velocity is, our dependent variable. We're testing out the effect that force will have on that for circular motion. And if you collected really good data, and I found there were some glitches in that simulation, but generally what we should see is a graph that might be something like this. So you might not have seen that. It might look linear. Sometimes you have to manipulate your scales and zoom in or zoom out depending upon the scenario. So we could talk about that in class on Monday um, if you didn't see that exact graph or whatever the next day we have class that is. So once we have that, we definitely see it's not linear. And there is a curve. So anytime you have a curve, it's like a square root or an exponential change. So we need to linearize that. So whenever you have a curve, if you square your vertical axis, your y-axis, that will straighten it. So any curves like this, if you square that axis, it'll straighten it. And it is a positive, relationship. It's a positive slope. So we don't have to do anything to our x-axis. So going up in this area here, to linearize that, I'm going to kind of just zoom in so that we're just on experiment one. If we would to square our velocity and then graph the force, again, no need to go through and do this with your data, but if you did do this to your data, it would give you a straight line. And the reasoning why I don't ask students to do this, one, under normal circumstances, in this lab, the data turns out very poorly just because of human error and not being able to, make things move consistently, and also the timing is very difficult. So now the analysis for that. So we're looking at the relationship between the two. So we start off, we have a line. Let's write, let's put our math hats on, and we're looking at like y equals mx plus b. We don't need to worry about the b because there is a 0, 0 mark. So let's put our physics hats back on. So change maybe here. So our y-axis is measuring velocity, which is squared. The slope of our line, we don't really know what the slope is, but whatever it is, it's going to be like, change in y over change in x. So it's going to be, v squared over f, but we want to see what that actually equals. So we're not going to put that in yet. And our x-axis is measuring our force, which we can kind of call centripetal force, or in the case of this lab, it's that tension from the string. So we're going to pause there for a second. I know we need to find out what our slope is here. So that's where this next part is going to help us out. Show the combination of your constants that equals the slope of your graph. So that's a little hint that something with our constants is going to fall into, representing our slope. So from what we stated before, kind of move that down here. So we need to do what's called unit analysis. So velocity is measured in meters per second, but we have that square in there. So it's going to be meters squared, seconds squared. Force is measured in newtons. But anytime we have a unit that is named after somebody, a newton, a pascal, a joule, a watt, all these units that we're going to come to figure out later in the year, if it's named after a scientist, it's not the real unit. It's not the real representation. So we need to break that down to see what it actually is. So in Newton, when we think of like F equals ma, mass times acceleration, a Newton is really a kilogram times a meter per second squared. So we have some common units we can get rid of. The seconds cancel out. One of the meters will cancel out. And we are left with a meter over a kilogram. Okay, so nothing else to kind of break apart. So in our lab, what did we measure in meters? The only thing we measured in meters was radius. Kilograms. What was the only thing that we measured in kilograms? Now I know there were two masses. There was the masses associated with the washers, but that was really, how we changed our tension force is the weight of those washers. So we're not looking at that necessary mass, but big picture, what's moving? It's the stopper. So did we measure the mass of the stopper? Sure we did. So that was the mass of the stopper. So when we kind of look big picture here, these were our two constants. So if we wanted to check the accuracy of our lab, I could have had you, take the slope of this line, like actually plot this out, do like v squared over r, or v squared versus f, and go take these two values here, and that should be, if we did, radius divided by mass, the slope of that line. So that's why I asked you to write those down. So then going into our proposed general equation, usually this comes about like after we do experiments 2 and 3, but I'm going to go ahead and do it now, just to kind of help you guys out. Those highlights annoyed me. So in this, we can now get rid of our question mark and state that our slope was our radius over our mass. And that's our equation for that specific graph. And also that's going to turn into our physics equation. So we're going to rearrange that a little bit. So we did mention at the beginning of the unit that this is kind of like Newton's second law, but just for circles. So if we rearrange this equation here so that it is force equals, which is, a centripetal force or a tension force, once we rearrange that, we move the radius and mass to the other side of the equation, and they would like flip around because we're going to divide. So you would wind up getting mass times v squared over radius. Okay, so you're thinking big deal, Mr. Ford. This is the neat part though. So we also mentioned, let's move this down a little bit, that Newton's second law for circles is really just the same thing. Mass doesn't change, mass is mass, but it's going to be a centripetal acceleration. So in analyzing this, we've also defined an equation for centripetal acceleration. So you could still do like Fc equals mac for circles, and then define centripetal acceleration as v squared over r. So nonetheless, we developed an equation for centripetal force, Newton's second law for circles. So that's the goal, to be able to develop that equation for the other two experiments. So before you do that, I'm going to need to kind of help you out with the graphs. So for, mass and velocity, our graph should look kind of like, hold on one second, this is messed up a little bit. So we're doing velocity and mass, velocity and radius. So this one should look kind of like this as a curve. And again, sometimes you need to squint your eyes a little bit on your graphs to see if it is a curve. And unfortunately, with this simulation, we couldn't change the masses that significantly. I think it only went up to about 300 grams or 0.3 kilograms. That's not a whole lot of mass or weight. So in the lab, we go up into like almost like 2,000 grams. Because the more you vary your data, the space between your data, the more detailed or dramatic the changes will appear. So even though it might look like a line, if you zoom into it, you might be able to kind of force yourself to see those curves. For the velocity versus radius, it's going to look just like our first graph that we did. So since the last one, the velocity versus radius looks just like that, we can go ahead and just say we're going to square that y-axis and radius will stay the same there. But then for this one, the middle one, we do have a curve, but it's also like an inverse relationship. And we want to have so all of our graphs are, positive. So since it's curved for this graph here, squaring the velocity will make it straight. So if we just simply squared, I didn't want to have you guys peek at that. So if we square this, it would then straighten our line. That's an inverse relationship. So to get rid of that inverse relationship, if we take the inverse of our x-axis, it will then make our graph positive. So that's the correct linearized graph for mass and velocity. So squaring the velocity and taking the inverse of the mass will give us that. So now that we can all have that positive slope for each experiment, you can then go ahead and attempt to complete the equations for each one, just like we did before. Like you might not have the slope or what that slope represents, but through looking at your units, just like we did here, like we started off saying, it was velocity squared over force. Well, what are those units? Does anything cancel out? And see what we are left with. So go ahead. This is also the homework, is go through here and see if you can complete those. We will likely have to discuss this though next class. If there's any questions, be sure to send me a Schoology message.